All right, it's time. So let's continue. Let's see what we have. All right. Dun, 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 dun. We were talking about Laplace transform. All right. So we were talking about solving second order differential equations. Okay. This is what we have for a homogeneous harmonic oscillator system. Once we have this, inevitably we are going to deal with not only just exponential, but also cosine and sine. So a natural question to ask is then, how do we know the Laplace transform of sine cosine? And we have all kinds of ways of doing it. The first way to do it is take the Laplace transform. Actually, go ahead and try to do this integral using integration by parts for twice, deal with the ending points. And finally, eventually you will have some ideas about what this is. But since we already know a lot of nice properties about Laplace transform, so instead what we did is we took the d-tool. We know sine omega t satisfies the initial value problem. That is y prime prime plus omega y equals 0. We know both sine and cosine satisfy this differential equation. So the difference between them will be the initial condition. This will work for sine, and this will work for cosine. Same equation, different initial conditions. Y0 equals 1, y prime 0 equals 0. Okay, this works for sine omega t. This works for cosine omega t. Then what we do is we actually go ahead and apply Laplace transform. Solve the algebra. In this way, we have find the Laplace transform for both sine and cosine. If you repeat the process, square, here's a square, here's a square. Ly equals 0, S, L, y prime prime. I'll remove 1 prime. Plus omega square Ly equals 0. And S, L, y minus y0. Together, it gives you Ly prime minus this plus omega square Ly equals 0. Okay, let's clean everything a little bit. We find S square Ly minus sy0 minus y prime 0 plus omega Ly equals 0. So finally, S square plus omega square Ly equals sy0 plus y prime 0 divided by s square plus omega square if you just divide this one on the other side. Okay, that's the process we did before for sine. Now you can see this one also works for cosine. The only difference is you plug in a different y0 and y prime 0. So for sine, it's going to be s times 0 plus omega divided by s square plus omega square, which is this. For cosine, it's the same formula, but different initial conditions. So we have s times 1 plus 0 divided by this, which is s squared plus omega squared. Same process, different initial conditions. We have the Laplace transform of sine and cosine. All right. That will be what we need. Surprising or not surprising, everything just looks so nice. For example, if you just look at the Laplace transform for both, do you realize that this one square plus this one square still equals 1? Okay, that's a nice property of sine cosine. It's beautiful. Okay. Another thing you probably want to pay attention, that is, even though we have both, but notice omega is a constant. That refers to the, how to say, the natural frequency of the original, where this is. So that's the original frequency, natural frequency of the original spring. But S is a variable. So even though they looks exactly symmetric, actually this one is more like a x squared plus 1, and this one is more like a 1 over x squared plus 1. So they're a little bit different. One go with a constant, the other one go with a variable. But the good news is any linear combination of these two give you anything ax plus b, x squared plus y, so you can handle any kind of rational functions now. You have the x term, you have the constant term. That will be step 1. All right. Now with that in mind, let's try to do several examples. Okay. The first one will be something we can already do before. Now let's just do it with a new way. Damped harmonic oscillator. We have overdamped, we have underdamped, whatever. Okay. Let's take an example. Y prime prime, y minus 4, y prime plus 5y equals 0. I will skip the details, but roughly this is what we do. We have the eigen function. We solve for lambda. So s equals 4 plus or minus 16 minus 20, which is 1 plus minus I. Am I right? No, 2 plus minus 2i. Okay, that implies we have two solutions. The first one is e to the at, which is e to the 2t cosine t. The other one is going to be e to the 2t sine t. And then we take a possible linear combination. Depending on your initial value, you will be able to solve it. Okay, so that's how we do it. If we use how to say, the guess method in one dimension, or if we use the characteristic, basically eigenvalue and eigenfunctions in 2 dimension. Either way, it's solvable. All right. Now we want to use the Laplace transform. Of course, we need an initial value. Let's take y0 equals 0, y prime 0 equals 1. All right. Laplace transform. Use the linear property. So far, so good. First case. Okay. In addition, let's take this part. Okay, let's clean things a little bit. Sy0, okay, minus y prime 0, minus 4 SLY plus 4y0 plus 5ly equals 0. So you put the ly all together. We have the s squared minus 4s plus 5 ly equal equals sy0 plus 4y0. Oh, no, minus 4y0 plus y prime 0. Somehow. Yes. All right. Here. Yes. Here. All right. So ly equals what is it? That's y0. Okay. The rest is try to plug in the initial value. So this is 0, this is 1. All right. You know the answer is going to be sine and cosine related. Okay. That means this one somehow should be related to the Laplace transform we just computed. It's either this one, okay, or related to this one. Okay, or maybe both. So the first thing you should look at is probably just look at the top. You see, well, sometimes you have omega, sometimes you have s. Okay, for this case, you only have a number, so that should be omega. That means there's no such term because there's no s. Okay. Second, in order to do this, you somehow need to make sure they look similar. 1 is okay. You times a number, you times a 3. You times whatever number, you will make it omega, so that's okay. The trouble is actually what's going on in the bottom. This one is not an s square plus omega square type. Okay? With your experiences so far in calculus, every time you see something like this, probably completing the square will be a way. It may not work, but it's certainly worth trying. So let's just do this. Okay, moreover, this omega square is going to be 1. Okay, on the top you have 1. So you have omega equals 1. In this case, you have 1 and 1. That is fine. The only trouble is you don't have s. You wish this is s squared, but you have s minus 2. Okay. All right. So let's wrap up what we have. We finished everything. We end up with this. Now we're just looking for a inverse transform. We do know the inverse transform should be this. Somehow we don't have the exact same thing. Instead, we have this, where our s become s minus 2. That's the good thing about doing it with something we know. Because once you do that, you start to cheat a little bit. You do know the solution, right? The solution is e to the 2t times sine t. So you do know it's not sine t. It times e to the 2t. And what do you observe here? You observe a 2 here. Then it's not correct yet, but a reasonable guess is maybe this 2 come from here. Okay, we kind of cheated a little bit because we already know the solution. Maybe the thing come from here. So if I just have that, I will have a nice 1 over s squared plus 1. But if I now have this, I will have this instead. So this 2, somehow, maybe it will shift the whole thing here. Okay, so that's my guess. My guess is if I have a function, and if I multiply it with an exponential, and then I take the Laplace transform, my guess will be I will have the same Laplace transform, okay, which is fs, but the whole thing shifted by the exponential I just multiplied. That's my guess. You multiply by e to the 2t, you take the same Laplace transform of just sine t, but you shift everything to the right by 2. You multiply by e to the 3t, you shift by 3. That's my guess. Sounds good? All right. The rest is just try to verify our guess, or maybe deny, reject our guess. That is very easy to verify because L e to the at ft. Then you do the Laplace transform, dt. Okay. That is going to be, then you notice you can merge them together. S minus a. That's the left. this is the Laplace transform of f. What's the difference? Everything is the same, except this become that. That means if you multiply AT, it's simply just take your S and change it to S minus A once you finish. That it comes exactly from the multiplication of e to the AT and e to the negative ST. So this is correct. Verified. Sounds good? That is a fact. That means if you see any function shifted, you just multiply with e to the AT before you do the transformation. So now if sine t goes to this, then this one goes to e to the 8. Oh, we have a 2. So this one goes to e to the 2t times the original thing. Because shifting by 2 is the same as multiplying by e to the 2t before you do L. That's the answer. Does everything make sense so far? All right. That's how we do the damped, or with damped or without damped. Actually, we do everything in this way. Okay. Once we know the property of the Laplace transform of sine and cosine, we can do everything in this way. You can try more by yourself for examples. That's not the point here. I think everybody can do the algebra. But now let's take a second look at this thing we just did and try to see, did we discover something interesting? That would be always the fun part, right? So let's take a look. What did you do? You did this. You did Laplace transform and everything. You end up with something like this. Actually, let's just do this. And then you complete the square and try to do everything. Okay, that's fine. That's what we did. Okay. Does this look familiar? Do you remember if we do it by guessing, we have this? right? Or more precisely, what do we do? We do what? We do the eigenvalue if you just switch it to a system, and we have proved this, right? They're actually the same thing. So from here, you can see your characteristic equation is actually here on the bottom. Okay. Now, what's going on here? Well, things become interesting. You have three possible cases, remember? You have a quadratic. If you do the quadratic, how many different cases do you have? Number one, you have two real, right? That corresponding to two exponentials. Okay. You have two complex. And moreover, you have a degenerate case, which is not degenerate case, the generalized case, where you have a one repeated. One repeated root. That's where you have the generalized and the exponential one. You have two you have one eigenvector and then another generalized eigenvector. That's the whole thing, right? Sounds good? We know this before, okay? But now we can understand it in a different way. That means what? That means if you have two real, that means if you do the Laplace transform, you will end up with something on the bottom, like that. But that will give you two real. Two real means what? Two real means this one can be factored out into s plus 1, s plus 2. This one can be factored out into two linear factor. That's what we mean by two real, right? Now, how do you do that? You can further split it into this and this. That's how you do partial fraction. And now if you do the inverse Laplace transform of s plus 1, s plus 2, what do you got? You got exponential. No cosine, no sine. Sounds good? Okay, so two real solution corresponding to what? Corresponding to two linear factors when you do the Laplace transform, when you do partial fractions. What about two complex? Two complex means you have something irreducible. Make sense here? Moreover, you have something which is s plus 2. You can always complete the square. Once you complete the square, what do you mean? That means if you do this, your root will be 2 plus minus I. The 2 come from here. The I come from here. Does it make sense here? Okay, so when you solve a complex number, actually what you're trying to solve is this I tells you omega, which is the thing s omega plus omega square. That will give you the omega. That comes from the complex imaginary part. The real part actually give you a shift. And what do you mean by shift? Shift means multiply exponential in the original thing. So these two are connected. To be more precisely, I can change this to be general number SA plus omega square. That will be what you get. If you set this one to be 0, you will have S equal A plus omega I, okay, which is fantastic because this part gives you the omega in the cosine. This part gives you the shift. The shift gives you exponential. So no doubt, this is going to be e to the at cosine omega t or sine omega t. No doubt. Sounds good? Beautiful. Last case. What do you mean by you have one repeated root? That means you have something like this. All right. What's that? Do you remember how to do the partial fraction for this? Actually, I shouldn't put a 1 here. This can be something. Then you do this. That will be the most general case when you do the partial fractions, right, in calculus 2. Okay. And this part gave you exponential. Of course. The only thing you're missing here is this. Sounds good? And you know how to do it. Why? Because it's TET. Right? Before, how do we do it? We just told you maybe this one will work. We checked this worked. But now, actually, it comes from where? It comes from the Laplace inverse transform. Where you have some repeated thing on the bottom, which we will do later. It's actually not hard to do. But for now, this is the only gap we don't have. That is, this one equals this. All right. That's beautiful. Everything we learned before, now once you do Laplace transform, it becomes partial fraction. And this is actually calculus 2, or actually college algebra. Calculus 2 use this, but this is even before that. It's a college algebra. All you need to do is just have a rational function. You split it into partial fractions. You will either have a linear factor or a quadratic, irreducible quadratic factor. Linear goes to exponential. Irreducible quadratic goes to complex, which is exponential plus sine cosine. And if you have something other than s squared plus something, you just complete the square. And once you complete the square, you just shift the whole sine cosine by multiplying an exponential. That's it. Sounds good? Okay. We did the whole thing, and I did it on purpose, that I didn't simplify until the last step. From here, can you see what I'm trying to do? Basically tells you, well, no matter what, your bottom will look like this. Sounds good? So the only difficulty you have on the bottom is actually the initial and the both initial conditions. Okay, if you have an initial condition to be 2 or to be 3, you're going to have different top. And if you do that, that basically determines when you try to split this one into 2 partial fractions. You have A, you have a B times s minus 2. This goes to sine, and this goes to cosine. Sounds good? Okay, so the only thing the top does basically is try to determine if you split it into partial fractions, which part takes which coefficient. That's exactly the linear combination of both, right? And you have a C1, have a C2. C1 and C2 are determined by the initial condition. All right. Sounds good. Everything we learned about partial fraction before now can be connected. We still have 2 more left over. I will encourage you to think about this. I will briefly mention it. Number 1, can you have something like this? Number 1, we can. And we simply just do the long division first, remember? And then we do the partial fraction. This is how we do it. Now for dpq, we will argue this will never happen. And it's not hard to see. Qy. If you apply L, where does S squared come from? S squared come from here. S come from here. This one has nothing. This one is just Ly. So the constant, right? But you will only produce an initial value every time you reduce the derivative by 1. So why do you have a y prime 0 in your answer? The reason is because I have a y prime prime and I do Laplace transform once. Sounds good? In this way, other than the majority on the denominator, everything on the numerator will be one order less than the biggest one on the bottom, because every time you produce something on the top, you have applied the Laplace transform property for once. That is this property. That's how you generate S. Right? So every time you generate one of these, you use one of the initial values. The guarantee is this one will be fewer than what's on the bottom, because the one on the bottom has the most S. That's number one. Never happened. The second thing for you to think about is the classic one we have in partial fractions. Can you do partial fraction for this? Okay. Then let's not take this. Let's take just take a irreducible. Maybe, yeah. Okay. The answer is yes, we can do the partial fractions, right? Then when are you going to see cases like this? Now let's go back to that discussion we had before. Even for something with fourth order. Not square. Okay. If you apply Laplace transform, this one give you S4, this one give you S cubed, this one give you S square S1. Sounds good? Everybody has Ly. Okay, so eventually if you divide everything here to the other side, you will have something like this once you factor everything out. So basically we have a way to solve any order of DFQ using Laplace transform. Assuming, number one, you know how to do partial fraction. Number two, everything here is a constant. If you have a t times y prime, that's totally different. Okay? But a constant times y prime, because Laplace transform is linear, you can take the constant out. That's why. Okay? All right. Ho, 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 ho. It's beautiful. And we don't need more examples. Let's do the forced harmonic oscillator. Before we know how to do this, which we call a homogeneous case, if you do a linear system, it's going to be this. Okay, so we can focus on the eigenvalue, eigenvectors, and so on. Now what we want to do is we want to interfere it with an external force. Non-homogeneous. This is called external force. Okay. So how do we think about this in real life? Let's just think about it. Without external force, And clearly we don't have any frictions. So what you have here is a harmonic oscillator. That's just back and forth, back and forth, back and forth. Okay, no loss of energy. And you have a built-in frequency of 2. Fine. Now what you want to do is, not only every time you have a force from the spring, you want to add to the whole system another external force. Moreover, usually this external force is changing with respect to time as a periodic function. Can you imagine a case like that? You will have a force on this, and nothing changes as time goes by. It becomes bigger, smaller, bigger, smaller, bigger, smaller, bigger, smaller. An easy way to think about it is to think about this one is charged, positive or negative. Okay. Then I apply an electrical field to it. Then this one is going to receive an electrical force. Sounds good? Finally, I let the electrical field switch sign periodically, which usually happen when you have a generator, right? So we have, we have an alternating periodic. Actually, alternating means periodic, but either way, electrical field. Okay. And then another way you can think about it is actually you can add a vibration to something which already, some vibration which already exists. Okay, for example, you have something shaking on your table, and suddenly you have an earthquake, which is shaking the whole world. Okay, so you have two vibrations coming together. Sounds good? Okay, or maybe you have a string which is shaking together, and then you just take a big speaker. Okay, I don't know if that's a good thing to do, but if you have a string which is shaking, and you just take a big speaker right next to it and just play, I don't know, Uptown Funks or something like that, which has its own frequency. Meanwhile, we play the string, you will see the string is, after a while, the string is going to be disturbed by the external vibration. Okay, so those kind of things happen a lot. Now, if you think a little bit further, you already know something called resonance, right? If the external frequency you added to the whole system is the same as the natural frequency of the thing, the whole thing resonant, and finally they shake at the same frequency and shakes more and more severe as time goes by. We will do that right after this. Basically, to do that, you just simply have to take this and change this to be cosine 2t. Now you guys have the same frequency. Something terrible happened. Okay, but let's do this one first. How do you do that? Before we can't do it, but now let's try. Dum, dum, dum. All right. Y0 equals 0. Y prime 0 equals 0. Oh. There is a minus 0 here, but I just skip it because you have an initial condition which is 0. So it's not a mistake. S squared plus 3 squared. S squared this. Again, you should have a initial value, but again, it's 0 for simplicity. So let's just say 9. So finally, L1 equals S. Let me double check if I have the right thing, because the next thing is going to be long. And I don't feel like I have the right thing. Why don't I feel like I have the right thing? I should have the right thing. Oh, that's why I don't feel like, okay. I copied the wrong thing. It's 3 cosine t. Do I want to change that? Yeah, all my notes are based on this is 3 cosine t. I somehow wrote cosine 3t. That's why I feel terrible. All right. Somehow, I don't know why my screen stopped sharing, but this is what I mean. Okay. Yeah. In my note, I had 3 cosine t. Okay, somehow when I copy everything here, I got cosine 3t. Should I just go ahead and try to do this? Should I change everything back? Shouldn't be too... Yeah, I better change it back. I better change it back because I have the initial condition. It may screw up everything. Well, not too bad. 1 square. 1. 1 and 3. Everything else looks okay. All right. Okay. Partial fraction time. AS plus B plus CS plus D, S squared plus 1 should somehow produce 3S. AS cubed plus BS squared plus AS plus B plus CS cubed plus DS squared plus 4CS plus 40. That's on the top. Should equal 3S. Okay, that means A equals full C, negative C. There's no square. B equals negative D. B equals 4D. No, B plus 4D equals 0. So B equals negative 4D. And finally, A plus 4C equals 3 for the S term. Here and here. All right. The 2 in the middle give you 0, 0. A and C. A plus... Yeah? AS plus B squared, no problem. AS plus B, no problem. CS cubed plus DS squared. 4 CS plus, no problem. Okay. Let's not do this. Don't skip steps. Okay. Yeah, no problem. Okay. Plus b plus 4d equals 3s. So what did I do just now? I said a plus c is 0, b plus d is 0, a plus 4c is 3, and the b plus 4d is 0. Okay, this implies b plus d equals 0, b plus 3d equals 0. 3d is 0, so first d is 0. But if d is 0, then b is 0. So far, so good. A plus c equals 0. A plus 4c equals 3. So negative c plus 4c equals 3. C equals 1. That gives me a equals negative 1. All right, then therefore, this one becomes a is negative 1. Negative 1 over plus 1 over, no. Negative s plus 1 times s squared plus 1. All right. Everything here will be the side topic of how to do the partial fraction. Okay. This goes to cosine 2t. This to cosine t if you do the partial, if you do the Laplace inverse transform. Of course, this one comes with a negative. So finally, y equals negative cosine 2t plus cosine t. Coming from the inverse Laplace transform of this. All right. From here, we can see adding an external force really doesn't increase any difficulties for this second order ODE when you solve it using Laplace transform. What happened? You have this. That is the original frequency of the spring. So that thing still shake like that. Meanwhile, on top of that, you added another additional frequency. Okay. So we can easily just draw it. Where is it? Chrome. Decimals. All right. Without the external force, you have a nice shaking oscillator. Now with that external force, you combine two sound waves together. Okay, so what's going on here? Try to imagine. For some of the period, you don't actually cross the middle point. You just shake up to the middle point and then you go back. Okay. Sometimes they actually align with each other, so you shake over the midpoint and you go twice as far. Sounds good? So it totally depends on, is the whole field helping you to push further, or is the whole thing is acting as a friction to hold you back? And because you guys don't have the same frequency, sometimes it's helping, sometimes it's holding you back. That's basically what's happening with the oscillator. All right. Perfect. 205. That will be all for today.